Good evening, everyone. My name is Eric Allstrand. I serve as Associate Director of Admission here at Dartmouth College, and we are thrilled that you are joining us here, that you have chosen to spend your evening with us. We are so excited to extend a warm welcome to you as you think about joining the class of 2025 at Dartmouth. As many of you know, this was a very, very talented, exceptional group of applicants, and we are over the moon about the prospect of having you here in Hanover with us, joining this both social community, but this huge intellectual community. And you're going to hear a little bit more about that tonight. So I'm going to introduce Eric Osterberg, who's going to speak a little bit about what he does at Dartmouth. We are fortunate to be a place where the undergraduate is really at the center of what we do. Dartmouth College is Dartmouth College for a lot of reasons, and many of you wrote about that in your supplemental essays. And what makes Dartmouth so special is the people who choose to spend their time here. So I'm going to turn it over to Professor Osterberg, who's going to talk a little bit about what it means to be a professor at Dartmouth and the things that excite him about his scholarship.
Great, Eric. Thank you for that introduction. And again, congrats to all of you for the great news. Hopefully we can get you up to Hanover here coming in this fall. So I'm going to share my screen. And then, all right. So Eric, give me a shout if anything's wrong, but I'm going to assume that you see that all just fine.
You might want to do the swap displays. We can see down the road as to what's happening next.
Okay. All right. Not quite sure why that is, but there we go.
There we go. Perfect.
All right. Let me just pull up. All right. So the title of my talk here is Acqua Alta, the rise in extreme storms and sea level. I'm an associate professor in the Earth Science Department, and I'm a climatologist. So I study climate change on a lot of different timescales. And you might be familiar with the term Acqua Alta. It specifically refers to high water is what it translates from Italian, but high water in Venice in particular. But in this talk, we're not really just going to focus on Venice. We're going to talk about sea level rise across the world and this increase in storms, and look particularly at research that I've been doing with Dartmouth students here for the last decade or so. So of course, it's not just Venice where we see events like this. We now have what they call sunny day flooding in Miami Beach, where it looks like this, just like in Venice. There's no storm on this day. This is just a high tide, one of the higher tides of the month, and we have significant flooding here in Miami Beach. It's happening in Annapolis. It's happening really up and down the East Coast of the United States, even on our little tiny coastline of New Hampshire. The town of Hampton, New Hampshire, now has sunny day flooding. And the point is that none of these places used to have sunny day flooding, even just a couple decades ago. But what about something like this, right? So these sunny day floods, these are damaging, these are disruptive. But what about a time when maybe we're looking at 23 feet of higher sea level, when New York City might look something like this, or Miami Beach might look something like this? Is this even possible? Is this in our future? And if so, when? Right? These are the kinds of questions that my research group looks at. And of course, when we think of high water and flooding, it's not just raising of sea level, but lately we've also seen this really dramatic increase in extreme storms. Like around here, if in New Hampshire and Vermont, particularly in the Vermont side of the river, the recent storm that everybody thinks about is Tropical Storm Irene. It was Hurricane Irene down in the tropics, and it weakened a little as it came up here, but it dumped a tremendous amount of water and caused just devastating record flooding around here in August of 2011. And this is what it looked like actually just over the border in upstate New York. Or maybe if you're from the mid-Atlantic states, you're familiar with this event, Ellicott City, Maryland, just a couple of years ago in May. This was a massive flooding event, and this happened just 2 years after a very similar event in this exact same city in 2016. Or maybe if you're more familiar with the Gulf states, you're thinking about an image like this, Hurricane Harvey. Who can forget these images, right? Houston, Texas in 2017, where we had the largest rainfall ever seen anywhere in the country, over 4 feet of rain, 4 feet of rain from this single storm. So we want to understand what's causing these kinds of climate changes. So to do this, I use ice cores as one of my tools. So I'm going to take you here to the mountains of Alaska in Denali National Park, where we've been working for the last 12 years, actually, collecting ice cores and studying the climate. And so to do this, my students and I, we have to first acclimatize to get used to the high altitude. And then we take a helicopter from Denali Base Camp. This is the same base camp where all the recreational climbers are trying to climb Denali, Mount McKinley. And then the helicopter drops us up at our remote glacier field site here at the mountain right next to Denali. So the first thing we have to do is set up our field camp. You can see our drilling dome there, our kitchen tent, our sleeping tents. Everything's run off of solar power and wind power. And then we actually have to drill the ice core to study climate. And the way this works, I'm showing you the drill right now. The drill goes down the hole, collects 3 feet of ice, and then comes back up the hole. And we take that 3-foot long ice core out, which looks like that. And then we put the drill back down that hole and do that over and over and over until we go all the way to the bottom of the glacier, which is over 200 feet deep. And then we did that several times and collected 2 ice cores from the exact same site over a period of 6 weeks. And so once we get the ice cores to base camp again, we have to pack them into these airplanes and then pack them out to the little town and put them in a freezer truck. And that freezer truck then takes them all the way back here to Hanover, New Hampshire, where my students and I study the ice cores to understand climate change. So here we are back at that site here on the top of Mount Hunter in Denali National Park. You can think of this as our Denali campus. I've brought lots and lots of students to this site over the last 10 years or so. About 16 students have specifically gone here. These are just undergraduate students. Some of them are shown here. And these students are doing all sorts of things today. Tom here, he's now in law school. TJ here, he's now in med school. Patrick here, he went so many times he actually missed graduation because our field season here is June. So we had a little impromptu graduation up on the glacier. That's actually Mount McKinley in the background. Pat went on to work as a naval researcher, and now he's working at the National Climate and Atmospheric Research Center in Boulder, Colorado. Dom here, he was my first undergrad student ever. He's now a professor doing climate change research at UMaine. And Matt here, he's also a professor now at Colorado School of Mines. So these students are doing all sorts of different things, some in climate research, but not necessarily, but all getting to do this really incredible research, these sort of once in a lifetime kind of activities to support this work. And so what were we actually studying? Well, one of the things we're studying is how fast is the glacier melting up there? And how does that melting today compared to melting in the past? And so what we do is we can take this ice core, we can cut it in half. And what you're looking at is looking down on an ice core, on its side, cut in half. And the darker ice here is ice that has not been affected by any melt. Whereas these lighter bands here represent days during the summer when the surface of the glacier goes above freezing and the very top of the snow actually melts. And that melt trickles down into the cold snow beneath and refreezes as a solid ice layer. And so that's what these are. These are solid ice layers representing these days when it's above freezing. So you can imagine if you have more of these, that means that it's warmer. If you have fewer of these, then it's colder. You don't have many days above freezing. So this is what an ice core from 2009 looks like. And as we drill down through the glacier, we drill back through time. So this whole ice core that's 200 meters long, so 700 feet long, goes back, we think, about 10,000 years. And so if we just go back to the mid 1800s, this is what it looks like. We don't see barely any of these melt layers. And so this is just a little anecdotal evidence, but what we can do is actually look at every single one of these melt layers. And we had students measuring these and counting these and then plot them all up against time. And so on the left here is like 400 or so years ago, 1650. And then on the right is today. And each one of these colored dots represents one of those melt layers. And so what you can see is that there were not a lot of these dots back a couple hundred years ago, and then there's a lot of these dots today. So this is representing warming of this glacier, more and more melt. And when this came out a couple years ago, we got some nice coverage in USA Today talking about how we saw 60 times more melting on this glacier today than we saw just a couple hundred years ago. So of course, what's happening here is global warming. And global warming is something that has kind of followed me for my whole lifetime. And I've actually been interested in global warming for a really long time. So we can start 1977 when I was just a little babe here. And this is the global average surface temperature I'm showing, 1880s on the left, 1977 is shown on the right. And you can see that by then, we hadn't actually had all that much global warming. But go up to when I'm in 6th grade in 1989, and this is when I actually started first studying climate change and global warming. My actual year-long 6th grade science project was the greenhouse effect. And this was the same year that society in general was really first starting to notice climate change. Time magazine named the Earth its planet of the year instead of naming a person of the year. So this is really the beginning of the global warming environmental movement. You go up to 1999, I graduate from college, and this is when a famous hockey stick graph is published, showing that the warming that we've had in the 20th century is really unusual compared to the last 1,000 years. And it's called the hockey stick because it looks like a blade of a stick and the long shaft here. Move up to 2010 when I become a professor at Dartmouth, and ClimateGate is the big story, suggesting that all climate change research is just a bunch of bunk and the Earth isn't actually warming, and this is all baloney, despite the fact that the Earth just considerably continues to warm year after year. And then things really started heating up. In the last just 10 years, we jump up to 2016. We had this massive El Nino event. This warming just floored the climatological community. First, you can see this point in 2015. That blew us away at how much warmer that was in the previous record. And then 2016 happened, and that blew us away. And then over the last few years, we've been right at that same location. And so make no mistake that this 2 degrees of warming that we've seen, at least since 1960, all of the warming that we've seen is from human activities. None of it is from any sort of natural process. Before that, there's some contribution from natural processes, but after that, this is all us. This is all human-caused warming. And if you just look at the top, in this case, 13 years, it's remarkable. This past year, 2020, tied 2016 as the #1 warmest year, and you can see the records here. And so we know that this is all from humans since the 1960s, because we should actually be slightly cooling over the last, say, 40, 50, 60 years. And we know that because the only other thing that can really affect climate on these sorts of timescales is the intensity of the sun. And the intensity of the sun has been getting weaker and weaker since around 1960s. And so if there was no human CO2, which is shown in blue going up through the roof here, if we didn't have this human CO2, we would be slightly cooling as the sun got weaker for the last about 60 years or so. But instead, we've compensated for that slight cooling and then created this massive warming because of human CO2. So this is all us. And that change that I was showing you in Denali with the 60-fold increase in melting, this is what we're seeing on every mountain glacier around the world, or at least in every mountain region of the world. You can find the occasional glacier that maybe is getting a little more snowfall than normal, but you give it enough time and it's melting. And this is a science paper that came out in 2013 showing that there is no region of the world where glaciers are not melting. They're melting everywhere. One of the glaciers, another glacier that we go to, I take undergraduate students here every September on what we call the Stretch program. This is the Earth Sciences off-campus program, is the Athabasca Glacier. And maybe some of you have been here or heard about it. This is in Jasper National Park in Canada. And so we actually take students up onto the glacier. All right, this is an early cohort from, this is that 2009 group, I believe. Yep, we got the dog here. So that was 2009. And we can see how this glacier has changed, and we actually study how to do this kind of research. We teach the students how to do this kind of research on a glacier. And one of the things we learn is just how fast this glacier is melting. So this is what the glacier looked like 100 years earlier in 1917. And you can superimpose these pictures, and I've tried to line the mountains up so that the only thing that's changing is the glacier. And you can see how the glacier hasn't just melted back, but it's also dramatically thinned. And so we've actually lost half of the volume of ice that you can see in this picture here in the last 100 years. And we had an undergraduate thesis student who just finished up a couple of years ago who was able to project that basically all the ice that you can see in this picture will be gone by 2060. Okay, so this trend is continuing, and in fact, the trend's actually accelerating. So that's what's happening in the mountain glaciers. But if we really want to understand sea level rise and what we're seeing in Annapolis and in Venice and in Miami, we have to also look at the big elephants in the room, which is where the most of the Earth's ice is stored, and that's in Greenland and Antarctica, where you can see in Greenland, there's 23 feet of sea level stored there in the glacier. In Antarctica, it's over 200 feet, but we split Antarctica up into the western part and the eastern part. And most of it's in the eastern part, but we're actually more concerned about the western part, where there's 16 feet of sea level locked up. And so let's go to Greenland first. I've done a lot of research in Greenland, and in 2016 and 17, we did a snowmobile traverse that was over 2 summers. We spent basically 6 to 8 weeks in each summer. And we started down here at the star called Die 2, and we were collecting ice cores. Every one of these red dots is an ice core location and a place where we were camped for 3 to 5 nights. And so in year 1, we started at Die 2 and made it all the way up to Summit. And then in year 2, we started at Summit and made a big clockwise circle to collect all 16 of these ice cores. And each one was about 100 feet long. And the whole point here was that we were trying to study how fast is Greenland melting today, meaning over the last 50 or 60 years or so. And so this was the logistics. We were all on snowmobiles, five people, 2 professors and 3 students. We each had a snowmobile, and we had to carry everything that we would need for this 6 to 8 week trip. So that was not just all of our science equipment, but that was all of our camping equipment, all of our food, everything that we need to survive, including these little pods here. These were safety pods, just in case the storms came along that were too strong for our tents and we could retreat into the safety pods. Luckily, we never had to use those in these field seasons. But you can consider this sort of our Greenland campus, right? We're out there in tents for 6 to 8 weeks doing research. And we're out there. So we had to be completely self-sufficient. We're out there in the middle of the ice sheet, pretty much all by ourselves. You can see again, our kitchen tent is a big yellow one, our science tent next to it, little bathroom tent at the end, and then our sleeping tents, all oriented in a row like this, perpendicular to the wind so that we don't drift ourselves in storms. And then down here is where we're actually doing our research. And so here's a couple of students. This is Karina on the left and Gabe on the right, actually drilling one of these 100-foot long ice cores, which takes us about a day to drill. And so the story that we found here, we were looking at those same melt layers, was pretty much the same story that we saw in Denali, except things were just delayed a little bit. So in Denali, we saw things start to warm up in the beginning of the 20th century and continue to accelerate. But in Greenland, things are really just getting warmed up in the last couple decades. We don't really see this jump in melting until mid-1990s. And so the ice sheets take longer to respond to temperature. And so the warming that we've had over the past decades is just now starting to affect Greenland. And so we can expect Greenland to continue to accelerate its melting into several decades into the future, even if we're able to cool down temperatures in the future. It'll take a while. It's like a heavy freight train, right? You can't just turn the brakes on these massive ice sheets. It takes a while to get them going, and it would take a while to slow them down as well. And so all this melting ice from Greenland and Antarctica and these mountain glaciers, they're all going into the ocean and raising sea level. And this isn't just something in the future. We've already seen 7 to 8 inches of global sea level rise. And that's what's shown here with 1900 on the left, going all the way up to present day on the right. And the other thing to notice about this rise is that it's accelerating. So it was rising at around 2.5 inches per century in the beginning part of the 20th century, up to 4.7 in sort of the middle to late 20th century, over a foot per century if we go back to 93, and then now we're even higher at 17 inches per century. So it's getting faster and faster as we go through time, because Greenland and Antarctica are now starting to kick in. And so as we look to the future, we're looking at 4 to 8 degrees of future warming depending on our emissions. Do we significantly reduce CO2 emissions in the future, or do we dramatically curb our emissions? And do we reduce them, or do we continue on? So the red is continuing on as business as usual, which gives you the sort of 8-degree warming, and a reduction would get us closer to 4-degree warming. So one thing to notice is that no matter what we do, we're going to see more effects. We've already started seeing these effects. And even if we're able to dramatically reduce warming, there's still a lot more coming down the pipeline. But 4 degrees is a heck of a lot better than 8 degrees. And so we absolutely want to try and reduce emissions as much as we can to try and avoid the worst impacts. And when we look at something like sea level rise, it's a similar story. If we reduce emissions dramatically, we can see somewhere on the order of 1.5 feet of more sea level rise. If we continue on as we are with lots of carbon emissions, then we're looking at more like 4 or even more feet of sea level rise. And that's just by the end of the century, by 2100. So again, what we decide to do with carbon really matters. But no matter what, we're going to see disruptive sea level rise. In fact, we're already seeing disruptive sea level rise, right? That's what we're seeing now in Miami and in New Hampshire and in Venice. It's already happening. One of the interesting things to notice here is the really big uncertainty bars here on these higher emission pathways. And you notice there aren't big uncertainty bars going down, they're just going up. And so one of the questions is, why do we have so much uncertainty about just how high sea level can go even by the end of the century? And I want to give you a little taste of why we're a little uncertain about that, just on the upper side. And so I'm going to take you again up to Greenland. And this time, this is a trip that we took in 2012. This was 3 professors, 2 undergraduate students, and 2 graduate students. And we were up here in Northwest Greenland in a place called Thule. And we were studying both the glaciers. We collected some ice cores on the ice cap. And then we were also studying these lakes, which are right up against the ice cap. And we were collecting mud, sediment cores to study climate from those. So we were getting climate records from the ice and from the lakes. And I want to focus on this particular lake here, which is the one that's circled here. And we were sort of jumping around to all the different lakes around in this area. And at one point we were camped down here at the star at the bottom of the picture. And what you're looking at is looking down on an aerial sort of satellite image of the glacier. So here's the big ice cap at the top, and it's going off in a outlet glacier out to the ocean. And so this is circled that lake that I just showed you, which is here. And there was one night when we were at this camp, and we had to be on 24-hour polar bear watch. So somebody had to always be awake. And so we would take turns, everyone else was asleep and somebody was awake, making sure no polar bears came. They look really cute and cuddly, but you don't want to meet a polar bear in person. And so we all took turns, and the next morning over breakfast, we all remarked that we heard this really weird sound, like a river that was really close by, but there were no rivers close by. So the sound of rushing water. And it wasn't until about a week later that we were flying by helicopter from this camp up to another camp when we went by this lake again. And this is what it looked like on August 5th. And then this is what it looked like just 10 days later when we were flying back, after we heard the sound of rushing water. So I want to draw your attention to this part right here. And that part is the same as this part here. So notice this sort of change in the tone of the ground. It goes from dark brown to lighter brown. That's the old lake shoreline. So this whole lake catastrophically drained underneath the ice cap and then out to the ocean. And then when that happened, this whole huge section of the ice cap collapsed down into the lake basin. And this all happened in the span of probably 8 to 12 hours-ish. And this is huge. So just to give you a sense of scale, the distance from the shoreline here down to the bottom was around 160 feet. And this whole lake was about a mile in circumference. And so this is what it looks like from helicopter. You can see this whole ice cap is collapsed into where the lake used to be. And we think the water used to be underneath the glacier, supporting the ice a little bit. And then the water finally found a way out to the ocean, which is off to the left here. It tunneled its way out to the ocean. And once it had a cave, a sort of channel system out to the ocean, all the water just catastrophically drained. And then this massive depression in the glacier and this huge canyon opened up. We actually, before we understood what we were really looking at, we didn't have a chance to really understand it. We actually walked right out to the edge of this thing, which was not smart. But luckily we were all fine and got some amazing perspective of just how big this thing is. And we can see it by satellite now. This is huge and it's still there. And what this shows us is that when you mix ice with water, solid ice with liquid water, things happen fast. These glaciers can catastrophically melt and discharge water into the oceans. You can't catastrophically grow a glacier. That doesn't happen, right? That takes a long, long time. And this is what we see in geology. It takes a really long time to grow a glacier or to grow an ice sheet, but we can melt them really quickly. The question is just how fast will they melt? So when we think about something like this, Miami under 23 feet, the question is when will this happen? And, when we look out beyond 2100 to say 2200, our best estimate is maybe 8 feet of sea level rise, but we have uncertainty that it could be as high as 28 feet of sea level rise. Then you go out to 2300 and, our best guess is 14 feet, but possibly up to 36 feet of sea level rise. And these numbers sound huge, but I want to tell you where they come from. These are not just from like climate models, okay? This is based on actually studying what happened the last time the Earth was this warm. We can go back 125,000 years ago. And for context, our species first showed up on this planet somewhere around, 300,000 years ago. So this is when we're sort of early hunter-gatherers. There's no city, there's no agriculture, there's nothing like that. We're just hunter-gatherers, mostly in Africa at this time. And it was about 2 to 4 degrees warmer because of slight changes in Earth's orbit around the sun. Now, this takes thousands of years. It took thousands of years to get to that warmth. Natural cycles take a lot longer than human forcing does. But we know that the last time it was just 2 to 4 degrees warmer, sea level was 16 to 26 feet higher, and this is what Florida looked like. And we know this because if you go to Miami today is sitting on rocks that formed underwater. These are coral reef rocks. They had to form underwater, and they all date to 125,000 years ago, right? These are Swiss cheese limestones. And so we know that if you give the Earth about 1,000 years at 2 to 4 degrees warmer, this is what will happen. What we don't know is just how fast that can happen if you turn the thermostat up a lot faster, which is what we're doing today. So we know this is the end point if we leave it there long enough, but we don't know how fast we can get there. And that's where the uncertainty comes from. So we're going to keep studying this and try and understand. This is the critical question that I'm focused on for the next, 5 to 10 years at least. How fast can these ice sheets actually melt? We know they will if you give them enough time. But what about the storms? So we've been studying the storms too. And for that, the research is really focused a little more close to home here in New England. I grew up outside of Boston. I went to school, my undergrad was at Middlebury, and I've been here in the Upper Valley in Hanover for the last 13, 14 years. So I spent a lot of my life here in New England. And so we've been studying how these extreme storms are changing here in New England. And one of the really interesting findings that we had just a couple years ago, a paper came out in 2017, is that back in 1996, we saw some step change in these extreme storms. There was basically no change from 1900 until 1995. Some years were high, more extreme storms, some years were low, fewer, but there was no long-term trend. And then starting in 1996, we're in a new normal. And we jumped to see 50% more of these extreme storms. And these are the kinds of storms that cause flash flooding, that cause damage, the kinds of storms like Irene, like the Harveys, like severe thunderstorms that cause flash flooding, like severe nor'easters that cause flash flooding. They're happening 50% more since 96. And so the big question was, why? What was causing them? Was it more hurricanes? Was it more tornadoes? Was it more thunderstorms? What was going on? And so we, after finding this, we dug into it further with a bunch of researchers, and we were able to figure out that about half of that jump in 1996 was due to hurricanes. So things like Hurricane Irene happening more often. And that makes sense because as the atmosphere has been getting warmer and warmer with global warming, the oceans have been getting warmer and warmer as well. And when the oceans get warmer, that's like fuel for hurricanes. Hurricanes run off of warm water and water vapor, and both of those increase when the ocean and the atmospheric temperatures go up. So the trends that we've seen lately, like the record-breaking 2020 hurricane season, where we ran out of letters, right? We had to go into the Greek alphabet because we had so many tropical storms and hurricanes. This is what we expect to see into the future as oceans continue to warm. And it's completely consistent with what we're already seeing today. And so research is starting to come out that's looking at individual storms. And what we're understanding is that, sure, something like a Hurricane Harvey could have happened in the past, but what climate change is doing is it's loading the dice. It's making it much more likely, in this case, 3 times more likely, that something like Hurricane Harvey can happen. So, maybe in the past it happened once a century, but now it happens once every 30 years. That's a huge change. And we also know that as the temperatures go up, that we can increase rainfall. And so the research shows that we boosted rainfall from Hurricane Harvey by around 15 to 20% because of human-caused climate change. And that's a massive amount of damage that was increased because of it. What was interesting about our research is that we found it wasn't just the hurricanes, though. It turns out that thunderstorms were a big part of this story, too. So about a quarter of the jump that we saw was from more of these thunderstorms. So half was the hurricanes, a quarter was the thunderstorms. And around here in New Hampshire, we've seen a lot of these. Interestingly, particularly on July 1st, it seems to be a really bad day in the summer around here. We've had 3 July 1sts, 2013, 17, and then again 2019, where we've had massive downpour thunderstorms that have caused flash flooding and infrastructure damage. This was a brand new housing community that got flooded and had this massive landslide into it back in 2013. This is just in Lebanon, New Hampshire, the next town over. This is in Orford, New Hampshire, just 2 towns north. And the one in 2019 took out the towns, just 2 towns to our east. So what's interesting is we think this is caused by a jet stream, which has gotten wavier than it used to be. And that tends to give you more extreme thunderstorms. And I mentioned that Ellicott City flooding. Well, we had a paper that just came out last year that showed that because of human-caused climate change, this event was 1.5 times more likely. Again, we're loading the dice for these kinds of events to happen more frequently. Sure, they could have happened in the past, but now they're happening more frequently. And then it turns out it's not just the hurricanes, it is not just the thunderstorms, but it's the nor'easters as well. All 3 of the kinds of storms that give us flooding, all 3 of them are becoming more frequent or more intense. And so the 15% of that jump turns out to be from these nor'easters. And again, that's associated, we think, with this wavier jet stream. And we've seen sort of dramatic examples of this in 2018, where we had 4 nor'easters come up the East Coast and whack Boston and Rhode Island and the coast of New Hampshire in just 1 month, in 3 weeks, in fact. 4 storms in 3 weeks. It was just remarkable. And we just, like 4 hours ago, I got an email saying that a paper that is in review right now just got accepted. And we were looking at these changes since 1996, the same group of scientists, and we're able to actually attribute this to human-caused warming. So it's not just that this has happened. It's not just that we understand why in terms of what kinds of storms are changing, but now we've actually been able to attribute it to human CO2. And so that paper should be coming out in a few months. And so what's interesting is, we've talked about sea level rise and we've talked about storms like they're sort of 2 different things, but of course they come together, right? Like the worst flooding that we see is usually associated with these coastal storms. So for example, Boston, before those 4 nor'easters in March, we had an even bigger nor'easter in January of 2018. This was equivalent to the 100-year flood. $1 billion in losses. And this is what downtown waterfront Boston looked like. The aquarium is just off to your right here. And so if we look at a map of what that flooding looked like from this 2018 nor'easter, again, this was the #1 highest flooding that Boston has ever seen. And you can see that quite a bit of downtown coastal Boston here was inundated, causing that $1 billion. But now let's think about this exact same nor'easter, but happening in 2070 under sea level rise. And then this is the amount of flooding we get. Same exact nor'easter, but now we're compounding the problem with the melting glaciers and ice sheets, right? And you can see just how much more damage somewhere like Boston would experience with something like this. Another way to think about this is to take that 100-year flood, which is what we often use as a benchmark, and think about how much more likely is that to happen? How much more frequently will that happen? And an extreme situation here is in Miami, where the event that 50 years ago happened on average once every century, the flood level that happened on average once a century will happen 2 to 3 times each year. So again, that's a combination of sea level rise and these changes in storms. 2 to 3 times each year for the 100-year, what's now considered the 100-year flood. And that's just by the year 2055. That's not even looking out to 2100. So these are remarkable changes that we're seeing. the combination of sea level rise and this intensity, this increased intensity of storms. And so one of the things that I've been focusing on lately is not just understanding the problem, but figuring out solutions. What are we going to do about this? And so, my research, what I get paid to do as a professor and as a teacher, is focusing on understanding the problem. And a lot of my volunteer time outside of work is spent looking on solutions. And so I'm a founding member, and I'm now the vice chair of this group called the Upper Valley Adaptation Work Group. And what we're trying to do is bring together everyone in this community who's interested in this. So this is town leaders, this is NGOs, this is students at Dartmouth, this is company leaders, anyone who has interest and a stake in this, to try and make this area more resilient to climate change and to try and reduce climate change by reducing our CO2 emissions. And so, for example, one of the things we do is we hold this community academy where we teach community members and town leaders about the problems and about the solutions, and then let them become leaders and catalyze increased action. And in fact, tonight I was running double duty. I just jumped out of a 2CLA session that I was running a little bit early to come join you guys here today. And what's really cool is that we've involved Dartmouth students. So, maybe you're not into earth sciences, maybe the climate science isn't your thing, but you're still interested in climate change. And so we're working with students, 30 students just in the past few years, are working with this group on various aspects of the project, right? Some of them are thinking about psychology. How do you engage climate skeptics and speak in a language that they want to engage in? We had filmmakers create a film about flash flooding and the importance of culverts. We had writers working on children's book to teach kids about climate change. We had people who are working on organization. How do you organize communities like this? We had somebody who was a group of students who were trying to create an app that would help people figure out how to reduce their own CO2 emissions based on, very personalized. What's the next thing that you personally can do to reduce your emissions? We had a group of students investigating Lyme disease. They were interested in public health. And so they were looking at the connection between Lyme disease and climate change. And then we had some design students. They just finished this project. They were helping us come up with a logo and some branding for this UVA organization and for the 2CLA, that community academy that we have going on. So regardless of what you're interested in, we're engaging with students across campus. And I know for a lot of students coming into Dartmouth, there's a lot of uncertainty about, how do you interact with professors? How do you get involved in research like this? And this is my last slide. And what I wanted to do here is just give you a sense of undergraduate students that I'm working with right now. These are students that in the past couple of months, I'm meeting with on a regular basis, usually on a weekly basis, some of them a little less frequently, depending on their project. You can see that they range from freshmen, like Jessna, who had just reached out to me by email. She was in my class in the winter term, and she reached out and said, I'm interested in doing some research. So we're actually having our first research meeting tomorrow, and she's interested in metal pollution. I've got a sophomore, Eric. He's working on wildfire and climate relationships, and he took a class with me in the fall term and then started research in the winter. Said, hey, I'm really interested in this stuff. Is there anything I can work on? We have this brand new project that was just funded to look at wildfire relationships. I've got Abigail, Chantal, and Liam are all juniors. They've been working with me since their sophomore year. They all took classes with me earlier on and were interested, and they're working on research from the North Pacific to Greenland. I've got some seniors doing senior projects or senior theses. One, Andrew's working on sea level rise in Providence. He's from Providence. He's passionate about it. Kat's working on Antarctic ice cores. Jacob's looking at that wavy jet stream. And then I've got students who have now graduated, but I'm still working with them. So Max just finished his thesis in the winter term in December, in the end of the fall term, and he graduated, but now we're publishing his research. So we've been in weekly meetings. We're just about to submit his work for publication next week. Ursula, she's now a PhD student. She worked with me for 3 years here. Now she's a PhD student at UW, and we're trying to publish some of her research. So we're in communication, and we're not just publishing what she did, but she's actually doing new work now to add to that. Pat, he worked with me forever. He was that guy who graduated on the glacier that you saw. He went off and worked for the Navy for several years, and now he's working as a researcher, and we're trying to publish his research as well. And then Dom, He was actually my very first undergrad student back in 2008 here at Dartmouth. I was just a postdoctoral scholar at that point. I wasn't even a professor. And then he ended up doing a PhD with me. He's now a professor at the University of Maine, and we work on pretty much everything together. And in fact, he's now a committee member for my graduate students now. So what I want you to see is, these students are working, some from freshman year, some join senior year. Whenever sort of is right for them, they can start working with me. And a lot of these students, we end up working on things beyond their time here at Dartmouth. And a lot of these students, I'm not listing them here because there's just a lot of other ones, but they go on to do totally different things. So even if you don't want to end up doing climate research afterwards, the kind of tools and the skills that we're teaching you are applicable to all sorts of different careers after Dartmouth. So I'm going to wrap up there. I'm just going to leave this slide up, but I'm happy to take any questions that you guys have.
Awesome. Thank you so much, Professor Osterberg. That was excellent. And we have a lot of great questions. And for the folks in the audience, the way this is going to work, we'd like to hear from you. We like to have a little bit more engagement, as was already mentioned. Professors and students get to know each other really well at Dartmouth. So we want to still promote that when possible. So I will get to the questions. And if I get to your question, I'd love to call on you. I'll unmute you, and then you can ask your question directly to the professor. But to give you a moment to kind of level set, and again, keep submitting those questions. A great question that came in that you kind of already talked about a little is, what are the classes that you teach at Dartmouth?
So I teach classes all through the spectrum. I teach a very introductory course called The Evolution of Earth and Life, and we look at the whole evolution of the planet from its beginnings all the way up till today. I teach meteorology, and that's a sort of freshman or sophomore level course. And then I teach that field course, The Stretch on the Glacier, which is a junior level course. And then I teach an advanced climate dynamics class, which is more juniors, seniors, and there's some grad students who are mixed into that class as well.
Awesome. Claire had a great question. Claire, I'm going to unmute you, and you can ask your question of the professor that's kind of related to some of that field work that you do. So go ahead, Claire.
Oh yeah, thank you. I was just wondering, you said the holes, the ice cores that you take are sometimes over 200 feet deep. I was just wondering if that ever poses any detriment to the glacier.
It's a cool question, Claire. No, so it doesn't, the only thing that can potentially pose a problem are that with these really deep holes, and some of them go, the ones that we got from Antarctica, those are over a mile deep. And they take years to drill. The one in Antarctica that we work on from the South Pole took 3 years to drill. And so the problem is that the ice slowly flows. And so if you just drill a hole, the hole will close up. And so we actually have to put some fluid down into the hole to keep it open. It has to be basically the same density as the ice, but stay not frozen, stay melted. And so there can be problems. The only thing that I don't love about what we do is that some of those fluids are kind of nasty fluids. And so some places we have to remove the fluid. So like if we drill in a national park, they're very strict and say, you got to get all that stuff out of there. Right. So that's the only sort of potentially damaging thing. The other thing I think about a lot is, we're taking helicopter flights, we're taking airplanes. There's a lot of carbon that goes into doing this research, and we're very much aware of that. As you see, we try and do as much as we can with solar and wind whenever possible. Sometimes it's not possible. We justify it by we're trying to do a lot more good than the amount of carbon that we're burning in order to do it.
Great question. Thank you, Claire. Finn, you had a great question about what it looks like to get involved in those kind of adventures that students are going on. Go ahead, Finn.
Yeah, hi there. Thank you so much for the presentation. It's amazing.
Finn, where are you joining us from?
I'm from Norwalk, Connecticut, actually.
Oh yeah, right down the road. Awesome.
Yeah.
Go ahead.
Yeah, so I was super curious about these adventures you take your students on. I was just wondering what it takes to get to go on one of these, because I noticed you only selected, or maybe not selected, but only had 3 students with you on that snowmobile quest. So I was just wondering what it took to be selected, I guess.
Yeah, it's a great question. So, some of this work is pretty dangerous, to be blunt. We've lost some really very experienced climate scientists on some of these exact locations in the last few years. So we have to be extremely careful about safety and make sure that we take students who have the skills to be safe in this environment. What I love about the Denali work is that there's incremental levels depending on a particular student's skills and experience. So somebody who's completely inexperienced, has never been on a glacier before, can go up and spend 2 weeks at base camp and do amazing research with us at base camp and be very, very safe. And in fact, tourists, come in and out of base camp. People who have more skills can then go with us as we acclimatize up the glacier. And that is a little more dangerous. You have to have some skiing skills. You have to have some climbing and rope skills, skills with harnesses. And some students acquire those skills here at Dartmouth. Some come with some and then build their skills here at Dartmouth. And then for the students who have more mountain experience, we can actually take them up to that remote site. And some will start off at the lower, base camp, and then in a future year say, hey, I really want to go up there and develop that experience. And that's one thing that Dartmouth is really well known for, is our outing club, where students can learn these skills. And to be clear, I didn't have these skills as an undergrad. I had never been camping before. I think I went abroad my junior year and I went camping for the first time in New Zealand. I didn't start backcountry skiing and doing this glacier stuff until I was a graduate student. So everyone has to start somewhere. And we don't expect people just to come in with all this knowledge and skills, but the ones who are really keen and want to do this, we have the ability to train them up and get them safe enough so they can do this with us.
Yeah, that's a great point. And the DOC for sure is a great resource in that regard. Hannah Chipman, you had a great question that I think kind of ties together what a lot of the professor talked about and some of what his volunteer work has looked like. So would love it if you would ask your question.
Hi, so I was wondering, how do you deal with the frustration of producing so much evidence on the urgency of climate action, but seeing inaction and denial from people in power? And do your research efforts ever seem futile because of this?
No, it's a great question. I feel like it kind of comes and goes in waves for me personally, and it's evolved for me. I used to get involved in these debates with people. I used to even get in back and forth email exchanges with people, and I've just stopped. One of the things I've learned is, and actually psychological research supports this, is that it's very hard to change people's minds about something that they are firmly decided against. If somebody's ambivalent, unsure, uncertain, yes, you can absolutely convince them. If somebody absolutely does not believe in climate change caused by humans or believe it at all, I'm not going to say, there's nothing I can do to change their mind. And in fact, the more I go at them, the research shows the more they will believe what they already believe. So I just ignore those folks at the moment. And what's really heartening to see is that things are changing pretty quickly right now. I'm kind of blown away by the change in the current administration, the Biden administration. The way that they're approaching climate change is just night and day compared not just to the previous administration, but even to Obama, even to prior Democrat administrations. They're taking the right approach, which is, look, we can tackle this from literally every angle, right? The infrastructure plan, the $2 trillion infrastructure plan they just put out there, there's a lot of climate change stuff in there, right? But it's built as infrastructure and jobs because it involves everything we do. And this is the first time that the federal government has taken that level. But the other thing that always gives me is sort of my grounding is doing this local work where politics really doesn't come into play. When I go and talk to local towns, and it's not just because everyone up here is on one side of the political spectrum, because they're not, right? New Hampshire is a very purple state. And sure, Hanover is this very liberal little place, but you go one town away and there's people with all sorts of different political views. But when you talk to people about their experiences here, their lived experiences and the things that they're seeing, the fact that their roads and their driveways are getting washed out, right? That they can't go skiing in December like they used to. They can see it with their own eyes, and we don't have the same problems sort of speaking across the aisle when you deal with things locally. So for the last 4 years, that's where I've been focused, is right here in the Upper Valley where I can make a difference. And now that the federal environment is changing, maybe there'll be some opportunities to go bigger.
Thanks for that question, Hannah, and kind of ties into what Brendan Nyhan does over in the economic department. A great question came up, and I think it's a great one to end on, and it's maybe more of a personal one. Professor, why did you choose to teach at Dartmouth? You mentioned that you did your postdoc work here, but Dartmouth is a really unique place, certainly, but really an undergraduate focused place. So a little bit about what draws you and keeps you here.
That's a great question. So, I mean, this is going to sound kind of corny, I guess, but it's absolutely true. So I wanted, when I went to college, I was looking for the liberal arts experience. I went to a liberal arts school. I went to Middlebury College. And for me, I was looking for those small classes, that personal interaction with professors. My older brother went to a much larger institution that had, you know, I felt like he was just a number on a enrollment sheet. I wanted to have those personal relationships. And so as I was going through my, the beginning of my career in graduate school, I always envisioned myself back at a place like Middlebury, because that's what I knew and that's what I loved. And that's what I wanted to be able to do for my students now, was to have those same kinds of connections. And then I did my postdoc here, and I realized that what Dartmouth does so well is that we bring sort of big R1, so big time research, but it's all packaged in this small liberal arts experience. To me, it's the best of both worlds. Now, if I go to most, I would actually argue every other big R1 university, they do not emphasize teaching the way that we do. They just don't. Often graduate students are teaching the classes, or postdocs. There's not that personal connection. They're much larger classes. Teaching is not valued in terms of like how professors get promoted and that sort of thing. Dartmouth, we are required. This is who we are, is that we are top R1 researchers, but we're also top liberal arts teachers working with undergrads. And I wanted to be at a place that actually valued my teaching. I wanted to be at a place that appreciated those things that I appreciated, while still having the ability to do really big time research, which means graduate students, it means postdocs, it means all the things that come with being a university, which frankly, a place like Middlebury doesn't have, right? And that's the difference between my experience here and my experience as a student at Middlebury. My research group of undergrads here, they're not just interacting with me, they're interacting with my grad students. And I'm able to bring in these really big projects to Greenland and Antarctica and Alaska, because we're a university with grad students and postdocs. But yet we still get to have these small interpersonal interactions. We still have these small class sizes, and teaching is central to what we do. So to me, it's literally the perfect fit for what I want to be able to do in my career.
Yeah, well, that is a beautiful way to end, and I really appreciate your time tonight. I'm going to drop Professor Osterberg's email in the chat. We had a lot of great questions tonight. We have a lot of budding Earth scientists among us who are going to be following up with you. And we really, again, are so glad that all of you tonight spent some time with us to learn more about what it would be like to call Dartmouth home in this environment. Be sure to keep an eye on your email. There are going to be a lot of additional programs. I believe we have one with a professor from government who's going to talk a little bit about that power of persuasion. So if you're interested in meshing this type of research with policy, keep a lookout for what that looks like. Again, thank you for joining us, and thank you to Professor Osterberg.
Thanks, folks. It's been a pleasure talking to all of you. I just popped in a little YouTube video about some of our Greenland work. If you're interested in that, it's kind of puts a little more color into some of the Greenland stuff we talked about.
Awesome. Thanks so much, everyone. Have a great night.
Take care.
Bye.